Welcome back. So, we have been discussing scalar couplings since last two classes. I hope you are all with me. You may please recollect what did we discuss in the last class. In the last class, I discussed about the interaction between two nuclear spins, the mechanism of J coupling, what happens, how the energy levels will be there when two spins are coupled or with a coupling constant 0 or coupling constant non-zero, and you worked out the energy level diagram for homonuclear spins and also heteronuclear spins, two couple spin system. And we also found out what are the possible transitions for two couple spins just by looking at the energy level diagram. We found out what is the total magnetic quantum number for each energy state and applied the selection rules. We could find out which transition I would say belong to which spin. So in a two coupled spin system, or I would say coupling constant 0, are two non-interacting spins. We observed there are four possible transitions, 2 for A and 2 for X. Since the frequency being same in both the spins, two transitions of A overlapped and also two transitions of X overlapped. As a consequence, what happened? We got only two peaks for two spins which are non-interacting. Today, let us continue further and see what happens if you bring in the coupling between these two. Okay, this is the case of a two spin half nuclei where chemical shifts are not same. That means they are not equivalent spins. They are not equivalent nuclei. Like another condition I have put, JAX is not equal to 0. There exists substantial amount of interaction between these two spins. The interaction strength is how much that we will decide later. But one condition is JAX is non-zero. And I have also put a condition, the chemical shift separation between these two nuclei is very much larger than the coupling constant. You understand what I mean? In the previous example, we saw two peaks for non-interacting spins. Chemical shift of X, chemical shift of A. Remember, one was here, one was here. And this separation you can measure. This is delta AX, difference between chemical shift of A and X. Let us say this is about 20 ppm. 20 ppm in 400 or 500 megahertz you take is 1000 hertz. Whereas coupling constant JAX is normally of the order of 15 or 20 hertz, less than that. This is the condition I am assuming. I am assuming the chemical shift separation between two spins is sufficiently large, very much large than coupling constant. Why I am going to do that? When you go further, after few classes, you will understand what is strong coupling, what is weak coupling, and how to get the transitions in a strongly coupled spin system, weakly coupled spin system. All those things we will discuss. Okay, at that time I will tell you all details, but at the moment simply understand what this is my assumption. Okay, now when these two spins interact, the magnetic energy gets modified now. Earlier they were not interacting. In the previous example, we had four energy levels: beta beta, alpha beta, beta alpha, alpha alpha. So there was all the energy levels for total magnetic quantum number of this energy state -1, 0, 0 and 1. So very easy to understand. Now when the spins interact, some interesting things do happen. Please understand. Now let us say magnetic quantum number of spin A and spin X have same signs. Means if alpha alpha both are same signs, plus alpha, What is the other energy state which has same sign? Beta beta. So when the magnetic quantum number of A and magnetic quantum number of X have same signs, that is alpha alpha and beta beta states are there, they are unpaired spins. You understand? They are unpaired. Only when they are opposite different spins, alpha and beta, they are paired. When they are unpaired spins, what happens? The energy levels are less stable. The alignment is less stable, because we know that, only when it is paired. You have studied in chemistry like Pauli principle, everything you know. It is now not paired. It is unpaired. As a consequence, to get themselves paired, it has more energy. If it is paired, it is less energy. When they are unpaired, alpha alpha and beta beta states will have more energy. Okay. Similarly, what happens to opposite spins, opposite signs? For example, alpha beta and beta alpha. Okay, alpha beta and beta alpha, these are paired spins. When these spins are paired, the alignment is more stable. Remember, alpha and beta beta, they were unpaired, they were less stable. But alpha beta and beta alpha are more stable states. So that means it has less energy. You understood the point? Always don't get confused. What happens with the interaction is there and non-interaction is there. There is non-interacting, there was no change the energy level. Alpha beta beta was here, alpha alpha was here, and alpha beta beta alpha. This is very clear. But when they start interacting, energy levels, something is going to happen. It won't remain same. What happens? Alpha alpha and beta beta has more energy, whereas beta alpha and alpha beta states have less energy. Now, because of this, there is a change in the energy of the states. Okay? When they are interacting, there is a change in the energy of the states. What is the change in the energy of the states? Alpha and beta are unpaired, gets destabilized. When they get destabilized, they push up by some energy. Okay? Alpha and beta beta, when they push up, destabilized, they go up. How much it goes up? It goes up by a factor of J by 4, where J is the interaction strength or coupling constant between A and X. So, by 1/4 of the coupling, they push up. Alpha alpha will go up, beta beta also will go up. That is a destabilized state. What about alpha beta and beta alpha? They are paired. When they get stabilized, they don't push up, they push down by the same energy. Understand the point now? Instead of going up, these two states come down by the same amount of energy. So alpha alpha and beta beta moves up, goes up, increasing the energy by J by 4. Alpha beta and beta alpha states, because they are paired, they get stabilized, they decrease in energy by J by 4. But the quantum of change of energy, pushing up or pushing down, is same. Both case J by 4. Okay, one case pushes up, other case pushes down. Please remember this point. Now, how it works out, let us see. These are the four. See, earlier I wrote four energy states like this: alpha alpha, beta beta, alpha beta, beta alpha, beta beta, like this. Four different. Instead of that, I am now writing vertically because I wanted to show you how the transition occurs. It's only a different way I am writing, that's all. But everything is same. Don't get confused. I am drawing in a different style to explain in a better way. That's all. Now, what are these four energy states? This is total magnetic quantum number of this state is -1. This is 0. This is 0. This is +1. This corresponds to beta beta, beta alpha, alpha beta, and alpha alpha. What did I say? These two states, beta beta and alpha alpha, they get destabilized. So pushes up by J by 4. Both this energy level went up. Look at it. It was here. They moved up by J by 4. So now They have a different energy level. Instead of here, they moved here, both of them. Now, what did I say for alpha beta and beta alpha states? They get stabilized and move down by the same amount. This goes by plus j by 4, comes down by minus j by 4. Same amount. They get stabilized by this energy. Now what is happening? The energy level, you see, now they are not identical to what would have happened without interaction. Because of the interaction, now energy levels and their separations are different. It is not same. Right? So, what to do? Now, let us see what is going to happen for these two now same transitions. What are the transitions? Now you know this is beta beta, beta alpha, beta alpha, alpha beta, and then alpha alpha. Okay. Now I am writing like this. What is going to happen? Apply the same selection rule. What are the allowed transitions here? The number of allowed transitions do not change. It remains same. 4 transitions are there. Identify which are the 4 transitions. This is -1, -1 to 0. This transition is allowed. Which is the transition? Beta x is getting changed to alpha x. See the difference? Beta x is getting changed to alpha x. So, okay, we'll start with this one. This one, alpha a is getting changed to beta a. This allowed transition because this also 0 to -1 and -1 to 0 is also allowed. Here, beta beta is not changing, but alpha a and beta a is changing. So x transition is not affected. So this is only a transition. X pin is not affected here. Now, what about the other one? This is also alpha a is going to beta a. And beta a is coming to alpha a. This also allowed transition from 0 to +1. The difference is 1. 1 to 0 again allowed. So -1 and +1 this thing, the change in the magnetic quantum number between two different energy states is +1 or -1 allowed. So what are these transitions? 2A transitions. But what is the change we are observing? Same thing we observed for uncoupled spins. Now what is the difference here? Look at it. This has moved up by j by 4. This has moved down by j by 4. This separation is now difference. If you take, it is j by 2, positive j by 2. You understand? It is j by 2. What about this difference? This is also j by 2. Now what is happening is one of the peaks is moving by j by 2, other is moving by another j by 2. See, now this is the chemical shift, let us say, of A peak, A transitions, A spin. Now, when it splits into 2 because of this energy level, one transition has higher frequency by j by 4, other has lower frequency by j by 4. I'm sorry, j by 2. Higher frequency moves from the chemical shift by j by 2, other has lower frequency by j by 2 because this energy separation is smaller, less frequency. So if this is the chemical shift of mine, what is less frequency? Less frequency is to the right. So this peak comes to the right. What about this peak? This is higher frequency, move to the left. So in the center, the peak which was there split into 2, and one peak moved to the right side, one peak moved to the left side by the same amount. This moved by to the right, this moved to the left by j by 2, this moved to the right by j by 2. And what is the difference between these two peaks now? You understand? Now what I am going to explain to you is this. Now there was a peak here. This peak is moved by here and this peak moved here. This is moved by j by 2 and this is also moved by j by 2. What is the difference between this and this? Is j. This is j coupling between A and X. You understand the logic now? This peak, central peak, split into two of equal intensity. This moves to the right. The one which moves to the right is lower frequency, this peak, and one moves to the left is a higher frequency, which is this peak. So we have two peaks. Now, because they are different frequencies, unlike in the previous example, there is no overlap. They are two distinct peaks with different frequencies. You understand the point? Now, what about this one? Now we will go to X transition. Now, what are the allowed transitions of X? You'll see this one. This is allowed because this energy state, magnetic quantum number 0 to magnetic quantum number -1 is allowed, the difference. But here, B is not changing, A is not changing, only X is changing. So, A spin is still, both these cases remaining in the beta state, whereas X spin is changing its state from alpha to beta and beta to alpha. And remember, this energy separation is a higher frequency because larger energy spread now. What about this one? Another one that is also allowed. Now this has come down by j by 4, this has gone up by j by 4. Now the difference is same, but now it is a lower frequency. Again, now what I am going to do is take this example. For X was like this earlier. Now because of this, one peak which is lower energy or lower frequency comes here, higher energy and higher frequency comes here. So these are the two doublet now, and this is, what is this separation? This is j by 2 and this is j by 2. What is this separation? This is j. Exactly like this, you get the same doublet. This is j and this is also j. And center of this is what? Chemical shift of X. And center of this is what? Chemical shift of A. And this separation is j. This separation is also j between A and X. So one of them is enough to get the j coupling, but both doublets are required to get the chemical shift. Are you all with me? I hope you will be able to follow what I am trying to say. Okay. I am now trying to tell you about what is the type of doublet you got. See, this is the one peak. Now after splitting it, see, the splitting pattern is, let us say this is j by 2, this is j by 2, and this is the line, and this is j by 2 and this is j by 2. Now this separation, I'll use a different color. This separation corresponds to j. Exactly what you see for this peak. Please remember, what you are seeing here is exactly same. Okay. Are you understanding? This is what it is. So now 1, 2 and 3, 4, there are four transitions are observed. What did you understand? Proton A will give two peaks. Frequency of one of them is increased by j by 2 and frequency of other is decreased by j by 2. Now go to the next one. Proton X also gives two peaks. In this case, what is happening is frequency of one of them is increased by x by 2, other is decreased by x by 2. Please do not get confused. Now, in this coupled case also, 4 transitions are there, but 4 are distinct. It will give you the coupling information, unlike in the previous example. So, two coupled spin systems can now give maximum of 4 peaks. That is what we understood. In the previous case also, whether it's coupled or non-coupled, j ax is 0, you give 4 peaks, but you detect only 2 because 2 overlap. Here you get all the 4 peaks. This is what is the example what we took for two coupled spin system. Now each P can be assigned to transitions. Remember, each P can be assigned to the transition. Look at this one. We observe what is one to two transitions in the energy level. Go back here. What is energy level transition from 1 to E2? This corresponds to alpha X is changing to beta X. So it is a X transition. And the X transition is what? This is energy is larger, frequency is larger. So that means it comes at higher frequency. This is X transition. What about 3 to 4 transition? Go back. 3 to 4. Again, alpha X is changing to beta X, but state of A is not getting changed. Both the spins in this case are A in alpha state. So this is a X transition, but with a lower frequency. So lower energy separation means lower frequency. So this corresponds to transition 3 and 4, 3 to 4. So this is center of this was the chemical shift of X. Now because of splitting, this moved to the right of J by 2, this moved to the left by J by 2. Let us look at A. Exactly whatever you happened at the X happened to A spin also. Now go back. Here what is the transition between 1 and 2? 1 and 3 is A. Similarly 2 and 4 is A. Yeah, 2 and 4 is A. So now look at this one. 1 and 3 is one transition for A, other is other transition for A. But always remember, the center of this doublet gives you chemical shift of A for here and chemical shift of X for this. Do not forget this. You understand how we got the doublets in two couple spin system for each spin. Okay. Now let us go further. We will try to understand something more. Very interesting thing we can do. We will go to the energy states for three couple spin systems. Very complex. If you have not understood how we get 4 px in two spin system, is even more difficult. Why? The possible energy states are much more here. How much was the energy states in the previous case? There are 4. There are 2 protons are coupled. Remember, it goes by the power 2 square. So you got 4 energy state. Now 3 coupled spin system, 2 cube. How much is 2 cube? 8. So there will be 8 energy states for this. The 3 coupled spin system. Let us again assume 3 spins, which are A, M and X. You understand? 3 spins A, M and X. I use the same letter. Don't take ABC. That's not allowed. Why? You will understand when you go ahead later. It takes another 1 or 2 classes for you to come to that point. At least 2-3 classes. You will not come to that. Afterwards, I will explain. You have to use only A, M and X because that is called weakly coupled. The chemical shift separation between them is larger than the coupling. So that's why I took AMX spin system. 3 I labeled as AM and X. Now what are the possible energy states for these 3? You must understand what is the possible energy state for these 3. One case, all the 3 spins of A, M and X are alpha, alpha, alpha. Now what is the total magnetic quantum number of this energy state? Alpha is half, half, half. Simply add up all the three, you get 3 by 2. Now you can come to a situation. I am now considering 2 alpha, 1 beta. You can also consider 2 beta and 1 alpha. That is another this thing. That's how 2 will have 8 energy states. Now consider the situation. This is alpha, this is alpha, this is beta. Then what happens? 2 plus half and 1 minus half, you will get plus half. Consider this possibility. Alpha, beta, alpha. That is plus half, minus half, plus half. Again you have plus half. In this case, beta, alpha, alpha. that is minus of plus of plus of, we get plus of. Okay. Now go to the other possible states. Now I am considering two betas, one alpha. So this is one possible combination. Alpha, beta, beta. That is plus half, minus half, minus half. If you add up all the three, you will get minus half. Okay. That is the important point you must remember. Now next situation. Beta, alpha, beta. This is beta, this is alpha, this is beta. What is the possibility now? What is the total number? What magnetic quantum number of this energy state? Minus of, plus of, minus of. It is minus 3 by 2. What about this one? Minus of, plus of. Beta, beta, alpha. This is beta, this is beta, this is alpha. So it turns out to be minus half. No. What about beta, beta, beta? All are 3 minus half. Minus half, minus half, minus half. All are oriented with spin states down. Then possibility add up everything, it is minus 3 by 2. Are you all with me? These are the only possible energy states. You find out any other combination is not possible. You will not get it. So when there are 3 spins coupled among themselves, the possible energy states are 2 cube. There are 8 possibilities. You can see. Now, which are the states which have same energy? Which are the states which have different energy? For example, this state and this state all are plus half. They have same energy state. Remember, all are plus half, plus half, plus half. Same energy state. This is 3 by 2. This is a different energy state. Similarly, this is minus half, minus half, minus half. All the 3 now have same energy. What about this is minus 3 by 2. So, how many energy states you can think of? Only 4 different energy states, out of which one is 3 by 2, other is 3 by 2. The remaining 6 energy states, out of which these 3 are of equal energy and these 3 are of equal energy. So there are 8 energy states, out of which 2 are distinctly different like this, and these 2 are distinctly different in such a way these 3 have plus of energy and these 3 have minus of energy. I'm sure you are able to understand. I hope. Don't get confused. I don't want to repeat. You understood. Now this is, you can work out yourself. Possible permutation combination you would have studied. Okay. So if you work out that way and you will have found out what are the energy states here. This is what it is. Now I am going to write the energy levels and transitions in a AMX spin system in a very simple way. I said minus 3 by 2 state here, which is minus half, minus half, minus half. All the 3 are down. This is plus half. All are 2 up, 1 down. All are 2 up, 1 down. You see, this is minus. Here 2 down, 1 up. So this is a minus energy, minus half energy state. And what about this one? This is plus 3 by 2. Okay. So now what we will do? We'll find out what are the allowed transitions. Please remember, what are the allowed transition? Change in the total magnetic quantum number between energy states must be either plus 1 or minus 1. Apply the selection rule. Minus 3 by 2 to half. Is it allowed? Of course it is allowed, because minus 3 by 2, if you take the difference, it is going to be 1. Or this way is also allowed. Similarly, this to this is allowed, and 3 by 2 to 3 by 2 is not allowed. So this to this allowed. All these states can have a transition from this. All these 3 states can have transition from this, and all these 3 states can have transition from this, because plus half to minus half, minus half to plus half is 1 is allowed. So there are various combinations of transition which we can think of, what are allowed and what are not allowed. Okay. You understood what I am trying to say? Let us take one example of one transition. What is this? X of alpha x is changing to beta x. Allowed. because plus 3 by 2 to half, difference is 1. 3 by 2 minus half is 1. So this is allowed transition, correspond to x. What about this one? Alpha x to beta x plus half to minus half allowed is one transition. So this alpha of x coming to beta f, beta of x is going to alpha x, both are allowed. Okay. Now go to the next one. This one, alpha of x coming to beta of x, that's allowed. Go to the next one. So alpha of x again is going to beta of x. And find out there are no other transitions corresponding to x possible here. All are m and a, and only x transitions are only these 4. No other transition is allowed. Look at it. All are am and only 4 possibilities like this. That means you got 4 transitions for x. You understand? What is the energy separation between them? You can work out like the way we did for 2-spin system. Okay. Now let us see what is this. Here A is undergoing transition from beta to alpha, alpha to beta. What about these two? Remaining same. They are not getting disturbed. What about this? That is allowed. Beta A is coming to alpha A. That is allowed. What about this? Again, what is happening there? Alpha A is changing to beta A. One more. This is also allowed. See? Alpha A is changing. So A has 4 transitions. Work out now. 4 for x, 4 for A. How many should be there for M? Exactly again 4. Look at this. Alpha f M is changing to beta of M. What about here? Alpha of M is changing to beta of M. This one, alpha of x is changing to beta of M. So like this, you can work out beta of M changing to this. So 4 transitions. And all these 4 transitions we can work out. So what I'm trying, we can discuss about okay, all the possible frequencies, and now we can calculate where do these peaks come. If I know the chemical shift of A, M and X, I can tell where 4 peaks are coming, which are the couplings involved, like that. So we will come to that. In the next class we will discuss these things. But today what I wanted to tell you is, I wanted to tell you the allowed transition in a coupled 2-spin system, how we can get the transitions, what are the 4 transitions. I explained to you alpha alpha and beta beta states are unstable states. They push up in the energy by J by 4. Beta alpha and alpha beta are stable states. They push down in the energy by J by 4. As a consequence, if you look at the allowed transitions, what you saw, 4 transitions, each are 2 for A and 2 for X. From the center of the chemical shift, one peak move to the right by J by 2, other move to the left by J by 2. Same thing for A, same thing for X. So now we extended the logic for AMX. We know there are 8 possible energy states, and we understood the transition probabilities, transition selection rules. What are the transitions allowed? We found 4 transitions are there for A, 4 for M and 4 for X. So how many lines we get? Totally 12 lines. So AMX 3-spin coupled, very weakly coupled, we get 12 lines. So what are the 12 lines? We understand when you come back tomorrow. Right now, this is the message. You please take it, you understand, and go back and practice some of these things. You will understand. So we will discuss more about the energy state and frequencies, everything tomorrow.